So today we're going to dive into a brilliantly simple yet really powerful new way to engineer one of the world's most useful materials, carbon film. We're going to break down this clever chemical trick that can turn a simple sheet of plastic into a precisely perforated, high-tech material. Let's see how they pull it off.
It kind of sounds like a riddle, doesn't it? How do you create perfect, intentional gaps in a material that's super strong and thinner than a human hair without just, breaking it? Well, that's the exact challenge we're going to explore today.
And here it is. This is the final product, a pristine carbon film with these incredibly precise holes. The amazing part, these weren't made with a laser or a drill or any kind of punch. Nope, they were created by making parts of the film literally disappear. So how on earth did they do it?
Okay, first, let's get a little context. Why is it so hard to work with these films in the first place?
You see, these films are a really big deal. They're strong, they're lightweight, and they're great at conducting heat and electricity. That's why we use them in so many advanced applications, from tiny nano devices to cutting-edge electronics. But that incredible strength also makes them a real pain to shape. The old ways of tackling this had some serious drawbacks. I mean, you could try blasting holes with a laser, but that can get messy and imprecise. You could try etching them with chemicals, but that's a really slow, complicated process. Or you could just try stamping them, which, risks cracking the entire delicate film. Clearly, a better, smarter way was needed.
And that brings us to this new solution, which completely flips the whole problem on its head. Instead of asking, how do we make a hole, these researchers asked, how do we make everything but the hole?
They call it chemical masking perforation, or CMP. And the core idea is honestly pretty genius. You start with a plain old sheet of plastic. Then you protect the spots where you want the holes to be, and you chemically treat everything else. When you bake it, the treated parts turn into super strong carbon, and the protected parts, well, they just turn to gas and vanish.
So here's a look at how the setup works. You've got your polymer film, that's the black layer there. It gets sandwiched between these masking plates. And see those little pillars? They're made of a non-reactive material like PTFE, which is basically Teflon. They press against the film, protecting it, while this reactive acid flows into all the unprotected areas. Pretty simple, right?
So how does this actually play out in practice? Well, it's a pretty fascinating three-step transformation.
The whole process has three main stages. First up is masking, which we just saw. Then comes the really key chemical step, stabilization. And finally, you have carbonization, which is just a fancy word for baking it in a really, really hot oven.
Okay, that second step, stabilization, that is the secret sauce here. The acid reacts with the exposed plastic, and it totally changes its chemical structure. The best way to think about it is like applying a fire retardant. This chemical change fireproofs the plastic, so that when it goes into the furnace, its carbon backbone holds together and forms that tough carbon film, instead of just burning up into ash.
And when we say hot, we mean hot. This film gets baked in an oxygen-free oven at 950 degrees Celsius. At that temperature, the unprotected, unfireproofed plastic just pyrolysis. It completely vaporizes, leaving nothing behind but a perfect hole.
All right, so that's the theory, but did it actually work? Let's take a look at the evidence. So this is what the film looks like right after the acid bath, but before it goes into that super hot oven. You can clearly see the chemical reaction at work. The areas that were exposed to the acid have turned black. That's the stabilized part where the molecules have been strengthened. And those bright, transparent dots, that's the original plastic, perfectly protected by the mask.
And here is the magic moment. On the left, you see that stabilized plastic film with the transparent dots. Then on the right, after it's tripped to the 950-degree oven, you've got a pure carbon film where those dots have become perfect, clean holes. It's a complete transformation.
And of course, they had the data to back it all up. Using spectroscopy to analyze the chemical bonds, the researchers found that the masked zones were nearly identical to the original plastic, while the unmasked zones were completely altered by the acid. The mask worked exactly as it was supposed to.
Now here's a little detail that I find absolutely fascinating. The whole thing shrinks. During carbonization, the film gets about 70% thinner, which is wild. It goes from 27 microns down to just 8. The holes also shrink, but a little less, by about 47%. It just goes to show you how dramatic this physical and chemical change really is.
So what's the point of all this, right? Why is a new way to make holes in carbon film such a big deal?
Well, this technique isn't just limited to simple little circles. By changing the shape of the mask, you can create these incredibly complex patterns. This one, for example, is a hexagonal design inspired by nacre, or mother of pearl, which is one of nature's toughest materials. It's biomimicry in action, learning from nature to build better things.
And the potential applications, they're huge. These perforations can act like crack arresters, stopping fractures before they spread and making brittle materials tougher. You could design custom composites with strength exactly where you need it. This could lead to new ways to manage heat and electronics, or even the creation of advanced foils that could rival the performance of carbon fiber.
As the researchers themselves put it, this isn't just some neat lab trick. It's a brand new manufacturing platform. It opens the door to designing and building carbon films with properties tailored for all kinds of high-tech uses. It's a fundamental new tool in the materials science toolbox.
All of which leaves us with a final thought. We just saw how this technique could mimic the structure of mother of pearl. And it really makes you wonder, with clever new methods like this, what other amazing structures from the natural world are we now one step closer to recreating? What's next?